Okay, so in class we talked about the charging of a capacitor when it's connected to this so-called RC circuit. That is a resistor and a capacitor and a battery, all in a series configuration. And we use this to kind of, this circuit to really analyze and understand what's going on in the charging process of a capacitor. Turns out this is a very important circuit because it's used to filter out frequencies and filter out noise. So we do want to understand it. The general setup for understanding this or for studying it in general, is to actually have like a switch here that will allow us to either create a RC circuit on its own, no battery source. So if our capacitor is charged, it'll let it flow. Let's draw a color. Draw this in a different color so we can differentiate the two. Or we can have the switch closed on the battery here, and that'll allow us to charge up the capacitor. So depending on which way the switch is oriented, we can either charge or discharge the capacitor. So let's kind of roughly understand what's going on here. Can I draw axes this way? Kinda. Let's see here. Okay, no matter which way I do it. Yeah, let's just draw it. Let's just go old school. Let's try to understand what's actually going on here. First, qualitatively, and then we'll do a quantitative look at it. So, let's draw a little mini RC circuit, in which case we'll have it. This is a little mini version there. And we want to look at the situation under a couple of circumstances. Paste it. Okay. So, to get a qualitative picture, we'll just make some arguments about what should happen in each of the cases here. So, what we're going to do is we're going to first have a capacitor which is just sitting there. It's been sitting there for quite a while. And then we'll connect the battery. We'll let it charge for a while, and then we'll disconnect it. So let's look at the battery voltage before we do anything else. Oops. So what's that going to look like? Well, it'll be sitting there doing nothing. At some point, we will turn it on, let it charge, and then turn it back off. And this corresponds to the following situations. Right here we turn it on, here we're letting it charge, and here we turn it back off. So we can look at what's going to happen in each of these situations. We'll look at the current. Get in the habit of writing a lowercase current. And that's the current through the whole circuit, right? Because our circuit is all in series. So the current through the capacitor or across the capacitor is the same as a resistor, is the same as the battery. So as soon as we close what we've done here, as soon as we close this switch here, what is going to happen to the current? Well, it's going to begin to flow. We'll call this the positive direction. And it is going to flow across and start decaying. as it charges, there'll be less and less, there'll be like 1 plus here, and 1 minus. There'll be less and less current flowing as this capacitor begins to charge. Why? Well, we can actually see what's going on here. As we're dumping more and more charges on here, and the current is decreasing, it becomes harder and harder to increase, to put more and more charges on there, until eventually it's so hard that no current will flow. So there's no current flowing, for example, through this resistor. And that means that there somehow has to be a voltage created by the capacitor that opposes the battery. So if we have a voltage gain from the battery, we have to have a voltage drop from the capacitor, because no current means no voltage is dropped across the resistor. And if no current is dropped across the resistor, Kirchhoff's laws, which tell us the sum of the voltage gains has to be equal to 0, tells us that when this capacitor is fully charged, there is a change in voltage across this capacitor. So around this region, around the end here, it's going to be completely charged, and then at some point we'll disconnect the switch, and now the circuit looks a little bit different. It only has a resistor and a capacitor, no sources. But now we have this fully charged capacitor here, which is equivalent to a battery facing the other way, and it's going to push current back as these charges redistribute themselves, and it'll just look opposite. So that's what the current is actually going to look like. How about the voltage? Well, again, we can look what will happen in terms of Kirchhoff's laws. Initially, the voltage should be 0, because the sum of the voltages has to be 0 in the circuit. But as we connect the battery, as this sucker begins to charge, we will have a rising potential of the capacitor until it kind of flattens out and reaches a constant equal to the battery voltage as the current goes to 0, as per our last argument. The the voltage across the battery will just be such that the sum of them are equal to the sort of the sum of the battery voltage, the resistor drop voltage, and the capacitor will be equal to 0. So that's what we expect, some kind of shape like this, like a rising exponential. But what happens when we disconnect it now? Well, when we disconnect it, the battery, and connect this kind of smaller circuit here, as the current is flowing the other way, that voltage is going to drop eventually to 0. We'll have, for the exact same reasons, we'll have like an exponential decay. And we want to understand these shapes. Well, we already kind of understand them qualitatively, but you can see that this plot doesn't tell you anything too rigorous. First of all, we're plotting current and voltage on the same scale, so you know it's a little bit shaky. And there's no absolute scales or times. We've just kind of plotted the rough shapes that we think these things should follow based on the physics of what's going on during the charging process. Okay, so let's look at these discharge and charge curves more quantitatively. In order to do this, we need to apply Kirchhoff's laws. So we need to look at the current through this whole system, and we can equate or relate all the voltage drops. There's going to be voltage gained at the battery, and then we're going to lose some voltage at the capacitor and some through the resistor. And as we said, as this capacitor is changing, the voltage is going to increase to counteract the voltage of the battery, and that'll give us the V in Kirchhoff's laws, and we know the voltage drop for the resistor is just IR. So we need to relate all these quantities, V and I and R. So in order to do that, in order to relate all these things, we can use our Q is equal to CV equation for the capacitor. And what that means, we'll write this in a more suggestive form. Q of t is equal to CV of t. And if I take the derivative, dq by dt, over dt. Well, that's just the current. That's the current. And that's furthermore the current through everything, because this is a series circuit. So the current through the battery is the same as through the capacitor, same as through the resistor. Recall that the current through the resistor is kind of misleading. If there's a parallel plate, there's an insulator between them. What does it mean, the current through the resistor? But as the capacitor is, I said resistor, I meant capacitor. What does it mean to have the current through the capacitor? As the capacitor is charging, you have current flowing into one of the plates and out of one of the other plates as the charge and discharge occurs. So if you just consider the capacitor as a black box, there's electrons flowing in and there's electrons flowing out. And the same number flowing in or flowing out because we have a series circuit here. So although you can't pinpoint an electron saying, oh, there it is to the left, oh, now it's to the right, you have an equal amount of current flowing into and out of it. So it's as if current is flowing through it. Anyways, just something that might confuse you when you think about it. So we have this equation. We got to finish the equation. dq by dt is equal to c dv of t by dt. And this is great, the capacitor, because this allows us to relate the voltage drop across the capacitor to the current, which allows us to relate the voltage drop across the capacitor to that of the resistor. And we know the battery voltage. So we can write Kirchhoff's law. Kirchhoff is now going to tell us, two H's, will tell us that the voltage drop across the battery minus the voltage drop across the capacitor minus the voltage drop across the resistor, and that's equal to the voltage drop across the battery minus the capacitor minus RC dVc by dt equals 0. In this little step here, all I did was plug in our relation between the current and dV by dt for the capacitor. And this guy here deserves a highlight because it is important. We can use it in both cases, in both charging and discharging our capacitor. So let's look at the case of discharging first. When we're discharging, choose a font which doesn't exaggerate my messy writing. When we're discharging, we have V battery is equal to 0, right? So this equation holds even when we're discharging the capacitor. It's just that we have a new battery here, this red line, which is a 0-volt battery. That's a long-winded way of saying we have a wire. But this equation is still true. This term here, VB, will just be equal to 0. And initially, V of 0, at time equals 0, the capacitor is going to be equal to whatever the voltage of the battery is, because it's fully charged. So let's look at our differential equation now. It now says, if we rewrite this, well, 0 minus Vc minus RC V, rather dV by dt equals 0, or V prime, I'll just drop the C subscript here, of t is equal to minus 1 over RC times V of t. And this is a fairly standard differential equation, which you can write the solution down for. I'm not exactly sure how this was done when you guys did your differential equations, or maybe you're just taking that stuff now. I'll just do it the way I remember seeing it. This is an equation that you've solved so many times you don't think about it anymore. After you've been in physics enough, by fourth year, you guys will just not even think. You'll just tell me the solution to this equation. But basically, one way of writing this is we can write this as dV by dt is equal to minus 1 over RC V. We can rearrange this as dV over V is equal to minus dt over RC, and simply integrate both sides. So it gives us natural log of V is equal to minus T over RC. And now we raise both sides, oh, plus a constant. Sorry, I almost forgot that constant. See, raise both sides to the power E. So we have V of T is equal to some other constant times e to the minus T over RC. Why did I multiply a constant? Because if I take the exponential of the sum of two things, it's just the product of e to the minus T over RC plus e to the constant, which is just some other constant. So finally, V of 0 is equal to, what did we say it was? V battery. And that's equal to, from this equation, that goes to 0, e to the 0, sorry. That's right, that's equal to 1 here. C1. So we can write our general solution, V of T, is equal to battery voltage e to the minus T over RC. Great. So that's good. When we discharge our capacitor, we see we have an exponential decay, which is, let's write this case here. So we now have our exponential decay, and we can see that the time constant, RC, we can see first of all the units of resistance times capacitance is time, which is interesting. But when T is equal to RC, let's write aside, T is equal to RC, V of T, V of RC actually, is equal to VB times e to the minus 1. That's approximately equal to 0.37 times VB. So that gives us a characteristic time scale of this system. So that's good. We know kind of fundamentally what's going on. We have very rigorously what's going on. We have an exponential decay with time constant RC, and this is called the RC time constant. Now charging is a bit more of a pain in the butt because we have this nasty constant, but it's pretty much the same idea. So let's look at charging now. Well, now we have V prime of T is equal to minus 1 over RC times V of T. Write this a bit neater. Negative 1 over RC times V of T, but we have this pesky VB over RC term here, right? I'm just rewriting this equation here now. So yeah, that's a bit of an annoyance because it means that we can't apply our last trick that we did to solve our differential equation. Whenever we have this kind of differential equation here, that's called a homogeneous differential equation, and they're often much easier to solve. And this, we have our homogeneous differential equation plus this little extra constant that doesn't have to do with our variable, with either T or V. It's just this constant, battery voltage over RC. That makes our differential equation inhomogeneous and means it's a bit more of a pain. But there's a very easy trick to solving this. There is a nice theorem in differential equations which says that if we can guess at a solution, if we can guess at a particular solution to, say, a homogeneous differential equation, and we guess right, then that's it, because solutions are unique. And if we have an inhomogeneous differential equation, and we can guess a particular solution to that inhomogeneous differential equation, the general solution to that crazy inhomogeneous DE is just whatever we guessed plus the corresponding solution to the homogeneous differential equation. Anyways, this is not a math class, but this is the kind of trickery that goes on in differential equations. So this just means that, let's just say we can guess a particular solution is a constant, say. Does a constant work? Does a constant solve this equation? Let's see. Suppose so. So V particular is equal to some constant K. Well, what does our equation say then? Well, V prime particular is equal to 0. So our DE will say, from up here, will tell us 0 equals minus K over RC. Remember, K is our guess solution, plus VB over RC. So that if that's true, our constant is equal to VB. So it's like, wow. That's how you solve differential equations? And that's why the mathematicians get paid the big bucks? I guess so. So that turns out it works. As long as the constant is equal to VB, then this perfectly well solves the differential equation. The derivative is 0. This, if V of t is equal to VB, we could have actually just read that right off. That also gives you 0, so the differential equation is solved. And now the general solution is what we found before, is V of t is equal to some constant times e to the minus t over RC. Remember, that's the solution to the homogeneous, plus VB. Initial condition. What do we say it was? Well, at time equals 0, what are we doing here? We're charging it. The voltage is equal to 0, right? T equals 0 equals 0. Because we're just charging it. It's totally discharged. We are here. So at that point, the voltage is equal to 0. So V of 0 is equal to C times e to the 0 plus VB is equal to 0. So that C is equal to minus VB. So using our general solution, V of t is equal to minus VB e to the minus t over RC plus VB, or V of t is equal to VB times 1 minus e to the minus t over RC. And that's our solution for charging a capacitor. Notice that at time t equals 0, we have 1 minus e to the 0, so that's 0. And it's going to rise until it gets to time equals, at time much greater than RC, as t goes to infinity. This exponential term goes to 0, and we'll get VB. So it'll behave like this, asymptotes to VB, which is what we expect. So in the case of charging, we get exponential decay here. And at charging, we get exponential increase, and discharging, we get exponential decay, which is consistent with these shapes. We just now know how to write them more generally. And that's about it for charging and discharging a capacitor.